Why does the floating point value of 4 times 0.1 look nice in Python 3 but 3 times 0.1 doesn't? I know that most decimals don't have an exact floating point representation. Is floating point math broken? But I don't see why 4 times 0.1 is printed nicely as 0.4, but 3 times 0.1 isn't, when both values actually have ugly decimal representations.
The simple answer is because 3 times 0.1 not equals 0.3 due to quantization, round off, error, whereas 4 times 0.1 equals 0.4 because multiplying by a power of 2 is usually an exact operation. Python tries to find the shortest string that would round to the desired value, so it can display 4 times 0.1 as 0.4 as these are equal, but it cannot display 3 times 0.1 as 0.3 because these are not equal. You can use the .hex method in Python to view the internal representation of a number, basically, the exact binary floating point value, rather than the base 10 approximation. This can help to explain what's going on under the hood. However, when you multiply by 3, the tiny little difference between 0 by 0.99 and 0 by 0.80, 0 by 0.07, magnifies into a 0 by 0.15 error, which shows up as a 1-digit error in the last position. This causes 0.1 times 3 to be very slightly larger than the rounded value of 0.3. Python 3's float repr is designed to be round-trippable, that is, the value shown should be exactly convertible into the original value, float repr f equals f for all floats f. Therefore, it cannot display 0.3 and 0.1 times 3 exactly the same way, or the two different numbers would end up the same after round tripping. Consequently, Python 3's repr engine chooses to display 1 with a slight apparent error.
Repr and str in Python 3 will put out as many digits as required to make the value unambiguous. In this case, the result of the multiplication 3 times 0.1 isn't the closest value to 0.3, 0 by 1.33333333333333p2 in hex, it's actually 1 lsb higher, 0 by 1.33333333333334p2, so it needs more digits to distinguish it from 0.3. On the other hand, the multiplication 4 times 0.1 does get the closest value to 0.4, 0 by 1.9999999999999 at 2 in hex, so it doesn't need any additional digits. You can verify this quite easily. I used hex notation above because it's nice and compact and shows the bit difference between the two values. You can do this yourself using, for example, 3 times 0.1 .hex. If you'd rather see them in all their decimal glory, here you go.
Here's a simplified conclusion from other answers. If you check a float on Python's command line or print it, it goes through function repr which creates its string representation. Starting with version 3.2, Python's str and repr use a complex rounding scheme, which prefers nice-looking decimals if possible, but uses more digits where necessary to guarantee bijective, 1-to-1, mapping between floats in their string representations. This scheme guarantees that value of repr floats looks nice for simple decimals, even if they can't be represented precisely as floats, e.g. when s equals 0.1. At the same time, it guarantees that float repr x equals x holds for every float x.
not really specific to Python's implementation but should apply to any float to decimal string functions. A floating point number is essentially a binary number, but in scientific notation with a fixed limit of significant figures. The inverse of any number that has a prime number factor that is not shared with the base will always result in a recurring dot point representation. For example, 1/7 has a prime factor, 7, that is not shared with 10, and therefore has a recurring decimal representation, and the same is true for 1/10 with prime factors 2 and 5, the latter not being shared with 2. This means that 0.1 cannot be exactly represented by a finite number of bits after the dot point. Since 0.1 has no exact representation, a function that converts the approximation to a decimal point string will usually try to approximate certain values so that they don't get unintuitive results like 0.100000000004121. Since the floating point is in scientific notation, any multiplication by a power of the base only affects the exponent part of the number. For example, 1.231e plus 2 times 100 equals 1.231e plus 4 for decimal notation, and likewise, 1.00101010e11 times 100 equals 1.00101010e101 in binary notation. If I multiply by a non-power of the base, the significant digits will also be affected. For example, 1.2e1 times 3 equals 3.6e1. Depending on the algorithm used, it may try to guess common decimals based on the significant figures only. Both 0.1 and 0.4 have the same significant figures in binary, because their floats are essentially truncations of 8/5 2 to the power of -4, and 8/5 2 to the power of -6, respectively. If the algorithm identifies the 8/5 sigfig pattern as the decimal 1.6, then it will work on 0.1, 0.2, 0.4, 0.8, etc. It may also have magic sigfig patterns for other combinations, such as the float 3 divided by float 10 and other magic patterns statistically likely to be formed by division by 10. In the case of 3 times 0.1, the last few significant figures will likely be different from dividing a float 3 by float 10, causing the algorithm to fail to recognize the magic number for the 0.3 constant depending on its tolerance for precision loss. Edit this URL.
If you want to